This is a very short revision session of two concepts that you must have heard a lot of by now, endogeneity and emitted variable bias, but it is so important for everything we discuss in this course. I want to make sure you have a very good intuitive understanding for it. Right, so the problem, these two concepts of endogeneity and emitted variable bias are deeply related to each other, and they're problems prevalent in observational data. And observational data is data generated in an environment which is not controlled by the researcher. And in these cases, parsing out causality is difficult, messy, and imperfect. There's substantial risk of bias, either over or underestimate the true causal impact of a program. And the majority of the remaining of this course will be looking at quasi-experimental methods that do not rely on experimental data to try and unpack that causal the cause behind programs. And terminology people often use in contrast to observational data is experimental data, where the researcher has randomly varied exposure to a program and the data itself. Right, so what do we mean with endogeneity? That's a word economists love using in seminars, and it means you're really in trouble if it's endogenous. So let's just go back to this estimating equation that you are very familiar with by now. Y is the outcome of interest. Let's say it's earnings. X is the independent variable. Let's just say this is college education. B is the value of Y when X equals 0. It's the average value of Y when X equals 0. And beta 1 measures this relationship between X and Y. The error term epsilon is the full extent of our ignorance. It is everything else that could explain Y that is not explained by the relationship between X and Y. So that's everything else. And so the problem of endogeneity is there might be other factors that are hidden in the error term in the sense that we can't measure it or observe it that explain variation in Y and is correlated with X. So that is really what we mean that these two, that epsilon is correlated with X, is that there are some factors inside of epsilon that drives Y, explains variation in Y, but it's also correlated with X. I mean, for example, if you want to look at the relationship between college education and earnings, it might be the fact that family wealth plays a key role in both of those. People born in wealthy families are more likely to get access to college education and also have more likely to be wealthy themselves. And in this case, the college education picks up both the causal impact of going to college and also the impact of having coming from a wealthy family. Intelligence or ability could also be a factor driving both. And what I'm actually explaining here is one example of endogeneity. Endogeneity could be any case where X is correlated with the error term. There's some factors driving Y that is also correlated with X. But the most specific example you will come across with a lot is omitted variable bias. And we also talk about selection bias a lot, but you can see selection bias manifests itself in omitted variable bias when you do regression analysis. Because selection bias, so there's some unobserved characteristics that you cannot control for in doing your analysis. And so this is just the mathematical outline of the omitted variable bias. I will never expect you to actually estimate it, but I think it's very good for you to have a deep understanding of it. And so let's say the true model meaning like this is everything that explains Y is a function of both X1 and X2, two different variables, and the epsilon term, call it V in this case. But now we cannot actually observe X2. Let's say this is ability and X1 is years of education. We cannot observe this. And so what we actually estimate is this equation 2. Equation 2 is Y is regressed only on X1 and not on both X1 and X2. And we're estimating these two different coefficients now, which are not necessarily the same as the true model equation 1 above. Right, and so we can actually estimate the size of the bias by running this auxiliary regression. And this is something that in the real world we'll never be able to do, because if we can run this auxiliary regression, we can also just control for x2. And there isn't a problem at all, it's unbiased. But going through conceptually through the step of auxiliary regression makes it very clear the mechanism through which having omitted variables can lead to biased estimates. And so the auxiliary regression is you take this variable you didn't control for x2 and you regress that on x1. And then now we have some kind of predicted, some value of x2 that's a function of x1. And let's just substitute that back into equation 1, right? So instead of putting in x2, we put in this new function delta 0 plus delta 1 x1 plus tau. And a bit of rearranging, and we see the kind of the constant term is beta 0 plus beta 2 times delta. And the coefficient on x1 is by beta 1 plus beta 2 times delta 1. And that is the key thing now, that when you estimate B1 emit with emitted, don't include x2, you're actually estimating these two terms here combined into one. And I think this quote actually from the Bailey chapter is incredibly useful and intuitive. It's when we emit x2, the coefficient on x1, which is now B1 emit, picks up not only B1, the effect of x and y, but also B2, which is the effect of the emitted variable x2 and y. But the extent to which beta 1 emit picks up this effect of x2 depends on delta 1, which characterizes how strongly x1 and x2 are related to each other. Right, now you're picking up by just regressing, for example, on years of education and not also on ability. This coefficient on years of education is capturing both the positive relationship between schooling and earnings and also the relationship between ability and earnings, but only to the extent that ability is actually correlated with years of education. Right. If there's a emitted variable which is completely unrelated to x1, let's say this is just your height. People who are taller have higher earnings, but this is not correlated with education, and probably is, but let's say it isn't, then there won't be any bias. Right. So let's go through exactly this example I mentioned. Imagine you want to estimate the impact of years of education on earnings, but you cannot control for ability, which is likely to be correlated with years of education. So delta 1 in this auxiliary regression would be positive. But we know, or we can intuit, might not be true, that smarter people, people who are more able, who perform better in school, also earn higher wages. They might make bad life decisions and become professors, but on average, they end up taking high earning jobs. And so now this coefficient on years of education captures both the impact of education and the impact of ability on earnings to the extent that years of education and ability are correlated. So this means you have two conditions that need to hold in order for there to be emitted variable bias. First, you need that the emitted variable is correlated with the independent variable, y. And second, you need it to be correlated with the included dependent variable, x1. So just take another example. If taller people have higher incomes, but height is unrelated to years of education, there will be no bias from including that variable. It's actually still useful to include it because it mops up some variation, but it's not necessary to include it for bias. So the implication is you don't have to worry about the fact that you can't control for whether somebody likes wearing Hawaiian t-shirts, for example. If we have a situation that people who like Hawaiian t-shirts are more educated, might be the case, but it has no impact on income, then there will be no bias from excluding this variable. So bias only comes from having both of these terms be non-zero, either positive or negative. In this case, you should actually not include this variable because it adds more noise. I'll get back to that in a moment. So let's go through one more example, which is in the Bailey textbook. And it's just looking at the relationship between years of education and economic growth. And say we want to estimate the impact of schooling on economic growth. And we have this equation. We have the dependent variable is growth of the country. We have a number of years, average number of years of schooling in this country. And we have a third coefficient, which is GDP in 1960. We control for that because there's a known relationship of convergence where countries that were poorer have higher growth rates and they catch up with richer countries, and that might be correlated with years of education. And so that also can account for some embedded variable bias, so we're controlling for that term as well. But one term that we do not have included here is the quality of education. And it might be the fact that how many years you're at school doesn't matter at all. It's just how much you learn at school. And it's just because years of education is actually correlated with quality of education that we actually do detect this positive relationship. So there's this amazing paper from Hanushek and Woosman who do exactly that. And so you see in the left-hand side, there is a positive correlation between average years of school and economic growth. So this is our beta 1 term if we had a univariate regression. But we see there is also a positive correlation between average test scores, which is how much a student has learned, how much they know, so the stock of knowledge, and economic growth. So, and finally, right, so this left-hand side here is beta 1. Beta 1 emit, if you don't include other ones. This one here would be beta 2, a positive correlation between test scores and economic growth. But finally, we also see here that there's a positive correlation between years of schooling and average test scores. So people who are in school for longer, countries that have people who are in school for longer on average also have children who have higher test scores. Right, now I want to ask you, what will happen to the magnitude of beta 1, the relationship between schooling and economic growth, if we have a model that also controls for student learning? So we have this beta 1 first. Is this over or underestimated? And what would happen if we also control for student learning? Well, the issue here is we know from that graph we just saw that there's a positive relationship between student learning and economic growth. And we could see from the most recent graph here that there's a positive relationship between student learning and years of schooling, right? And remember that this regression, when you have an omitted variable, is the true relationship plus the relationship of the omitted variable with the outcome variable mitigated by the extent of the correlation between the omitted variable and the independent variable of interest. And in this case, both beta 2 and delta 1 are positive. Years of education, quality of education is positively correlated with both growth and years of education. So we have an overestimate, upwardly biased effect, and that would actually go down after we included controls for student learning, because beta emit is larger than beta 1. So if you control for quality of schooling measured by learning, beta 1 would go down. And this is exactly what they find. So when they just, every time they control for log GDP, but when they just regress economic growth on average years of schooling, they have a positive, highly significant result. But when they add in this controls for student learning, you can see all of this result is actually driven by the relationship between student learning and economic growth. Really cool paper that kind of makes this really important point that it's about quality of schooling and not years of schooling. Right, so why do we really care about the omitted variable bias, because we can never actually estimate its true value, the size of the bias, unless we actually have the data, and then we don't have to care about, we can just include the model. Well, I think there are two reasons, 4 reasons. One is that it's a useful way for understanding endogeneity. X1 is correlated with the error term if X2 is hiding in the error term, i.e. it explains variation in the outcome variable, and X1 and X2 are correlated with each other. I think it draws a nice link between selection bias and omitted variable bias in regression analysis, because we can control for the relevant characteristics, then we will no longer have selection bias. And also, we can now make some intelligent guesses about the direction of the bias, right? Because in general, we kind of have an intuitive feeling about what the relationship is between ability and earnings and ability and education. So we can say, like, we think maybe this is upwardly biased and downwardly biased. I call that the known unknowns. But the other reason is, it's a bit more fundamental, is that it gives us a lot of humility and use of multivariate regression analysis. Just controlling for variables to take away the bias, is that there might be some other bias from an emitted variable that we did not think of. So always with observational data, you always have this potential challenges of emitted variable bias. I'm calling that the unknown, because you don't know what else could be lurking in the error term causing potential bias. And this is why economists are so afraid of the dark. They're afraid of this uncertainty of what's hidden in the error term that might be causing endogeneity, leading to bias. Right, and now just finally, I've talked a lot about how adding additional variables could change the estimated coefficient if there's emitted variable bias, and so you should add those variables as potential controls. But there's another reason why you want to add more dependent variables, even if you're not interested in its actual impact on the outcome variable, and you're only interested in the impact of variable X1. Adding more variables can actually help improve the precision of your estimate. So we actually discussed that a lot in the other lecture. It can shrink your standard errors. It means you have more statistical power in your analysis. And there's an equation in the textbook, but you don't have to know that. You just want to know there's 2 kind of rules of thumb. Is adding more variables will improve the precision of your estimated parameter beta 1 if this additional variable X2 is correlated with the outcome variable, but not too correlated with your variable of interest X1. Intuition here is it just kind of soaks up a lot of the variation, and there's kind of less variation left to estimate the relationship between X1 and Y. So it's kind of narrower confidence intervals. But it could actually worsen the precision if X2 has no relationship with Y, this variable you add, but it is actually correlated with X1. This is often considered the problem of multicollinearity. It's not a bias, but it just means that this variable is actually reducing the precision in the other variable when you control for it, add it in the model. The idea is just that it's adding noise. It's not soaking up anything. It's just like extracting from the informativeness of your policy variable of interest X1. So the implication here is, if you want to add control variables, only add ones that are actually correlated with the dependent variable Y. Right, that's it. That's a wrap. When we meet in person, we'll be going through some specific examples to just kind of nail down this intuition of emitted variable bias.